Thanks, Mark. Yeah, so we decided all talks should have a TLA title, meaning a three-letter acronym title. So this one is dual cube complex. Those who know what's coming know that this is not only dual cube complex. Yeah, so last time we talked about what are cat-zero cube complexes, and we talked about hyperplanes. And we saw the distance formula, but one of the things we saw is that each hyperplane, so if X is a cat-zero cube complex, and H is a hyperplane in X, then H is actually embedded the convex subspace of X with a cat-zero metric, also with the L1 metric that Leo was talking about, and it separates X into two components. Okay, and those we call, so I didn't write it last time, call them half spaces. So what we'll do first is sort of collect some combinatorial data about our cube complex coming from those half spaces. Okay, so this is we'll call the POC set of half spaces. Okay. So first of all, let's collect all of them. So I'll use curly H of X to denote the set of half spaces. Note that this maybe some we want to do drawings, and I'll want to do drawings later. Here's say my cube complex, and here is maybe some squares, and this is maybe a hyperplane. For a half space, what I'll do is I'll just put a little arrow telling me which side, is it this side or the other side. Okay, so this will be hyperplane. I usually denote hyperplanes with the letter maybe H or K, and the corresponding hyperplane, right, denote half spaces with H. The corresponding hyperplane I denote with a little hat. So what do we have on the set of half spaces? Well, we have the relation of inclusion, right? So let me just write H is less than K if just H is contained in K. Okay, I could have just written inclusion, done with it, but use this notation. And okay, so something like, and maybe here I have another half space. So H is less than K. This is great. And yeah, so what's the other thing we have is we have the complementation map from half spaces to half spaces. So what does it do? It takes a half space H to its complementary. Okay, so in the picture, if this was H, then this would be H star. Yeah, you all happy? Yeah. Can I just repeat the beginning of the question? Can I? So when I put a little arrow, this is the half space I'm thinking of. So H is really this half space.
He thinks you're picking one half space per hyperplane.
No, yeah. So right, when I have a half space, I can talk about the hyperplane corresponding to it. So that's denoted by H hat, and I can talk about its complement. That's there's no preference. I did not choose one for each yet. But see that coming. But okay, yeah. And now let's just collect facts about this map and this relation. Okay, so I have this triple. So we have the triple H. Okay, H, this relation, and this operation. and they satisfy. Yeah, so what do they satisfy? So first of all, this thing is a poset, partially ordered set. Okay. It's just inclusion. Okay, good. This, maybe I want to say a bit more about this poset. This poset has finite. I'll use the word intervals, but this should not be thought of the same intervals as Elia talked about. Yeah, so here I just mean that between any two, I don't know, H1 and H2, the set of all Ks in between them, this is finite. Okay. One can think of this set of half spaces. So if I have two half spaces, let's say K and H, or H1 and H2, then this set is exactly the half spaces that separate those. Okay. And there are finitely many of those. Okay, so this is one property. The second property has to do with this function, the complement. Let me put it here. So this function is fixed point free involution. Oh, sorry, order reversing involution. Okay, which is a lot of words to say. H star is not H. That's fixed point free. Yeah, for every H. Involution, right? And order reversing. So this is for every H and K. Yeah. Is it clear? Great. And moreover, so this is V3. We saw last time. So this was the last exercise I gave last time. Is that any set of pairwise crossing hyperplanes actually crosses. It has to live in some cube. Okay, and we limit our cubes to finite dimensional cubes. So yeah, the last thing would be, it does not exist an infinite set of half spaces such that so let's give it a name. I don't know, F in H, such that for every H and K in F, they are what I call transverse. So that's a new thing. What is this thing? This means none of the four possible inclusions happens. So H is not contained in K, but also H star is not contained in K, and so on. Mess it up probably. You just do this. That's fine. Okay, so this really supposed to be the case where the hyperplanes corresponding to H and K are transverse, are crossing. It's called transverse half spaces or hyperplanes. Yeah, so this would be, I mean, this is not exactly what we get by the way I defined Ket-zero cube complexes, but let's really think of finite dimensional Ket-zero cube complexes, and then you get something even stronger. You get that any set of hyperplanes that are pairwise transverse must be bounded by a certain size, right? This is really what, I mean, for most applications, this is what we want. Yeah, so this is maybe slightly stronger than what we have for the general definition. Yeah, we all happy? That too. So you mean with this square complex? Yeah. So let's see. For this square complex, what's the size of a set in which all half spaces are transverse. So let's see. Let's pick a half space. This is one. If I want something transverse to this, it's not here and it's not there. It's not this, not that. Yeah. So really, what I get is only this guy, maybe, or this guy. Okay. So here it's in fact bounded by 2. So that's exactly the point. So let's maybe say it. If X is finite dimensional, then such a set satisfies the dimension of the cube. Okay, so this is really, I mean, just keep this in mind. Replace this by what I said. This in fact is not really necessary for what's coming up, but it's more natural to assume this. Okay. Yes. So a triple satisfying those things for me will be called a POC set. In fact, it's a POC set with finite interval. I mean, all the properties that I added here are not always assumed. So finite dimensional and this finite width. Okay. So such a triple is called a POC set. Okay, so it's a POC set with complementation. We're all happy? So far, what we did is we started from a cat-0 cube complex, maybe finite dimensional, and we collected a bunch of data. And the maybe surprising thing is that this triple is all you need to know in order to reconstruct a cat-0 cube complex. Okay, so you can start with this completely abstract setting of a set, POC set with complementation satisfying those things, and build a cat-0 cube complex whose POC set of half spaces will be isomorphic to what you started. So the goal. So this is called the Roller-Sagiv construction. So this is really something that Micha did in his thesis, but this is an interpretation slightly more general than what Micha did due to Roller. And the goal here will be start with a POC set and then build a cat-0 cube complex such that the half spaces of X with the inclusion and complementation will be isomorphic. So really, this holds all the information one has about a cat-0 cube complex. Danny, you seem
tautological bijection.
Just a tautological bijection.
So why?
Why?
Yeah.
Okay, great question. Let's ask great questions. Right. Okay, that's a good question. Yeah, so I mean, the reason is we want to build cat-0 cube complexes, and it's much easier to give this type of information. A POC set, we'll see that it comes up as wall spaces and comes up in sorts of ways. And this will be a great way of getting new cat-0 spaces. Okay.
If you say this the bijection, you stated only one side. If you start with the cubic complex.
Yeah.
CCC.
Yeah, that's this is the starting point, right?
Yes. You construct the POC set.
Yeah.
And you reconstruct the CCC.
Yeah, that's the Roller-Sagiv duality. You can go back and forth, you get the same thing. Okay. As long as everyone's happy. Good. Yeah, so this is the duality. So you can go back and forth, you get the. Okay. So this is our goal. And now let's look at an example and sort of try to guess how to build this cube complex. Question?
No, sorry, I was just gonna, go on, sorry. I'll tell her later.
You should be asking questions. Yeah.
I was just telling her something I wanted to tell her.
Okay.
I was being distracted, sorry, I'll be better behaved.
Okay. So let's see. I mean, what I'm really going to draw is I'm going to draw the cat-zero cube complex side of things. Okay. And we try to reconstruct the things that are not present in the pocket of half spaces. So let me just do some example. Maybe we want to look at the hyperbolic plane tiled by, I don't know, some squares. So, tell me when to stop. You make the first mistake. Yeah, good. Thank you. Great. Right. So what do we have? We have the collection of half spaces, right? So here the hyperplanes are not really in this collection, but actually you can sort of find the hyperplane. So maybe just write it, although it's not going to be that important. So for me, the hyperplanes I denote by H with a hat. These hyperplanes. Yeah, so what would be a hyperplane given this very general framework? Well, okay, we know that each H comes with a complementary half space, and this pair sort of describes a hyperplane, right? Abstract. So this, you should think of this thing as being just all pairs H, sorry, right? Abstractly. Okay, but this is not what we care. We don't care about the hyperplanes. We really want the cube complex. We want to know what are the vertices, what are the edges, and so on. Okay, so let's focus on a vertex. So to sort of pinpoint a vertex in this picture, what I can do is I can just look at the collection of all half spaces pointing to this vertex, right? We do this thing. Okay. It's too late. No, I can. I can zoom in. I can.
Can't make everybody.
What? Cannot have. No, but I'll try. Vertex, right? V. And what I was saying is to pinpoint a vertex, what I can think of is I can think of the set of all half spaces that contain this vertex. Okay, so maybe let's call it U of V. Okay, so this will be the collection of all half spaces such that V is in the half space. Great. So what are the properties that this set has? Well, okay, see if H, so what are the properties? So if I have a half space in UV and I have a bigger half space, so in the picture, let me add some more. Oops. So maybe this is H and this is a bigger half space. Then what do we get? Well, if this contains V, then this should contain V. K should be there. Yeah. Okay, that's one thing. Another thing is, yeah, if H is in there, then H star is not in there, right? And moreover, so maybe let me write it slightly differently. So for every hyperplane, so this is a pair H and H star, the intersection with this UV is 1. This size 1, right? Because either H or H star is in V and not that. Okay. And maybe the last property I want to state is, this goes back to the title, DCC. Okay, so this is not really dual cube complex. This is the descending chain condition, right? If I have a chain of of hyperplanes. So every descending chain of things in UV must stabilize or must stop after a time. Stop. Okay, I cannot go on forever. Okay. And by the way, note that by the distance formula that we gave last time, we actually know that every two vertices are separated by some hyperplane. Okay, so the map V goes to UV is injective. Right? If you have two distinct vertices, they must have positive distance between them. And so it means that there is a hyperplane that separates them, which means that one of the half spaces will be in V and the other half space will be in the other vertex. So what did I want to write? This is injective. So really this is, I mean, I'm just saying this to illustrate that maybe this is the right notion. This kind of thing captures really vertices more. And that's actually the idea. So the idea is you look at subsets of the half space of the box set H. Okay, so let's give them numbers.
I have a question.
Yeah.
What do you mean by stabilize?
Meaning there is no infinite descending chain, properly descending chain. This is what where each such chain is actually finite. Yeah. So a subset U of my box set. Now I forget about cat zero cube complexes. I'm in this very general world of box sets. Is called, oh boy, that's going to be problematic, right? An ultrafilter, but this is not the ultrafilter that caused all of the problems yesterday. This is just for the sake of this definition. Should we give it a different name? Would make people feel more comfortable if we don't call it ultrafilter? Super duper filter. Yeah, let's call it U filter, okay? Just not to. Yeah, I mean, I should say ultrafilters are this thing that, I mean, you need the axiom of choice to know that they exist on like on N or something like that. Those things we saw, I mean, they're quite explicit. Yeah, one can write an ultrafilter. What? In the setting of cat zero. What? And they're kind of principal. That's true. But yeah. Great. A subset is called an ultrafilter if it satisfies 1 up to 3. Oops. It's called if it satisfies 1 and 2. Sorry. Maybe I should say this is called a filter. Okay, in this setting, this is called an ultrafilter or U filter for us. And this will be called the DCC ultrafilter. Okay. And so to build the cat zero cube complex, what we'll do is we'll take as the set of vertices, we just take all DCC ultrafilters. Yeah, so maybe what's missing here is we said that this map is injective if we start with a cat zero cube complex, but maybe it's not clear that this is onto. And this is maybe another exercise for you. Is show that if you take if you, or maybe let me just write V to UV is surjective when I go from vertices of the cube complex to DCC ultrafilters.
The definition
Yeah.
of filter, is that satisfied 1, 2 or 1, 3?
1, 2. 1, 2, sorry. And I'll say that, yeah, DCC ultrafilter satisfies 1 up to 3. So what do we actually need to show here is we want to show that the intersection of all the half spaces that form a DCC ultrafilter is actually attained by the vertex. Okay. Great. So these are the vertices. And maybe at this point you might already wonder why we even have such things, right? I mean, if we start with the general.
Sorry, yeah. So this big H here is that seem to have the Boston conditions you wrote there,
Yeah.
right?
Yeah. So I mean, this discussion was about ket-zero cube complexes. This is really about the general pocket. So H, this be the pocket, which again for me means already finite intervals. Yeah. So as a set of, remember the goal is to start with a pocket and build a ket-zero cube complex. So I'm building the cube complex. I'm telling you what are the vertices, what are the edges, what are the cubes, and so on. So vertices are just the set of all possible DCC ultrafilters. Right. So why do they exist? Well, okay, they exist basically because of property 3. You can see quite clearly that they exist. You just take a maximal such set, and you use this to build such an ultrafilter. So you take all of the half spaces in the set. For each one of them, you pick a direction, and you sort of fill it up so that it is an ultrafilter. And maybe I shouldn't say more. Okay.
So maybe
Yeah.
For the math student, really need the item 3. Because uncountable many hyperplanes,
Yeah.
it can still perfectly make sense of an ultrafilter.
That's true.
Yeah.
That's true. Yeah. The issue with infinite many crossing hyperplanes is that what we'll define next will not be connected, right? So the issue could be think of like an infinite collection of such hyperplanes, and I can choose whatever direction I want on them. This will be a DCC ultrafilter, right? As long as for each one of those hyperplanes I pick one of the directions, it satisfies all of those things. Yeah, but then the issue might be, connect the point where all of them are facing one way to the point where all of them are facing the other. And we'll see that this will be difficult. Once I give you the edges, you understand what connect means. Are we all happy with the vertices? Yeah.
Question, for this question is, do you also get all infinite dimensional ket-zero cube complexes? Because like in this condition tree related to like finite dimensionality, like do you still have this duality?
Yeah, so it's related to sort of like a local finite dimensionality. This could still be unboundedly like will not have finite dimension, but really just think of the finite dimension. Okay. So now what are edges? So I'll connect two vertices, so meaning two DCC ultrafilters, if they differ by one half space. So I connect U and V if the symmetric difference, what do I want to write, is just one hyperplane. So I switched H to H star. Yeah. So let's see it in the picture. We should have done it first. If this is V and this is U, right? Those are connected with an edge. What's the difference between UV and UU? Okay. Well, what's the difference? The difference is just this half space that's dual to this edge, right? So really the symmetric difference between the two ultrafilters for those two will just be replacing one half space with its complement. Right. So now you can think what happens in this case. Is the thing that I'll get will it be connected if I have infinite many? Okay. Next thing, we want cubes. So the idea here is basically you attach a cube whenever you can. That's sort of the general thing. Cat zero cube complexes, I mean, the cubes are really, every time you can fit a cube, you should put a cube. Hmm?
You don't really need them. If whenever they live, you just put them in.
Great question. I mean,
But there's a new perspective that we don't abandon cat zero cube complexes and just pull the meeting graphs. And I don't know if I fully agree with it, but that's where it comes.
okay, so this is a great question for Elia, but no, but yeah, you want to fill in the cubes. You want something that's simply connected. You want to feel this warm feeling in your heart where you know the space is contractible and it's cat zero and it's everything you hope for. I don't know. So, some guy told me.
Come on, you don't have to think about the questions if you want.
Okay, so when do we put a cube? So we put a cube when, okay, so I have, let's say, a vertex V, and I can find, so let's do a square maybe. So if I can find the one skeleton of a square, I should put a square. But what this really means is that whenever you have two hyperplanes, so H and K, okay, that you can replace independently, then you should put a square. Okay, so really the difference between V and this guy is replacing H with H star. The difference between V and this guy is replacing K by K star. And the difference between V and this guy is replacing both H and K by their stars. So this is exactly when, you remember this thing, when they're transverse. Okay. Okay, so that's the idea for cubes. So I did squares, but of course, same goes for more. Yeah, so this is maybe dual to some H and K and L or something. And why is it cat zero? So let me just sketch why you get a cat zero cube complex out of this. Well, okay, so one needs to show that it's connected. Maybe I'll leave that, so connected. But let's do simply connected, just a sketch. So what do we need to show? We need to show that whenever we have a loop, right, it's null homotopic. So I take a loop in this weird graph that I build. Okay, and I need to show that I can somehow homotop it to the trivial loop. And the idea here is very similar to the idea we saw last time for the proof of the distance formula. So you take, so what do we know? If I start at V and come back to V, right? And at some point I use an edge that replaces H by H star, I should use it again to go from H star to H, right? Because at the end I finish at V, right? Into a sudden. So every time I cross a hyperplane, I should cross it somehow again. Okay, this is not actually there, but for us, we should be thinking of that. Yeah. And then the idea is you do the induction that we did last time. So you look at the minimal length path that that has the same half space replaced on both ends, and you argue really the same. This edge here must have a hyperplane, say K, which must be transverse to H. If not, then again, along this path, I should cross it again. Right? This will give me a shorter path. So this is not the case. So K somewhere here. Yeah. But then by our definition of squares, we know that those two edges form a square, or adjacent edges of a square. Okay, and by changing, so now what can I do? I can homotop the path to this new path, and I reduce the length of a problematic. Yeah, same idea as last time. So this is one connected. This is maybe exercise. And finally, what do we need to show? So to show that it's a cat zero cube complex, we need to show that it's simply connected and that it is NPC or satisfies the link condition. Okay, so the link condition. So I claim that this is obvious. Why is it obvious? Well, to build this cube, what I did is I used the pairwise condition. Said this, so let's say H, K, and L. So I asked for each one of them to be transverse. What do I think? KL. Right. So if I see in my link, say a triangle, right, a 3-cycle, then it should be filled in with a Q. Just because it's something we check pairwise, so it's something that you can see already on the 2 skeleton. Is this clear? A bit rushed, maybe, but I want to show some examples. We don't have time. Okay, so this is how we build the ket-zero cube complex out of a pocket, right? And I claim that pockets are easy to produce. And so let's see some examples. So really, the most common way of producing pockets is by drawing some tracks. So maybe an example of this would be take a surface with a collection of curves on the surface. So it could even be one curve, could intersect itself. What happens when I pass to the universal cover, H2, this curve lifts to a bunch of arcs. And my drawings are sort of suggestive that this is what we should be imagining, right? So what I can do here is, for instance, say, okay, take as my pocket the collection of, so each one of those arcs separates into 2 components. So I can take the 2 components with the obvious complementation and inclusion. Okay, just like we build hyperplanes. Really, what I'm using here is the fact that this set has a product neighborhood. Remember this lemma from last time? Was that when we have a simply connected space with a subspace with such a product neighborhood, it separates connected. Okay, so what is the dual cube complex? So I need to sort of look at what are all possible ultra filters. So let's just do one of them. So you can see some of them. So if I pick a point in this plane, I can look at all the half spaces pointing to this point, right? This will be an ultra filter, just like it is in a ket-zero cube complex. It's possible that these are not all possible ultra filters. Yeah. So we'll see an example of this in a second. But anyway, so this should be a vertex of my dual cube complex, and let's see some edges. So if I change this half space, I get an edge. Okay, if I change this, I get an edge. Here they cross. I can change both of them, an edge, and so on. So really, what I'm doing is drawing a dual picture to the picture I start. Okay, so. And of course, I fill those things with squares, and so on. Is this clear? This is really the example you should have in mind. What I did not explain is why does this satisfy all the nice things that claim so, right? Why is this a legitimate pocket to start with? Yeah, the finite intervals and so on. And maybe say something about this. I have time. See that I do. But let's see what could go wrong even in this example, or not go wrong, but get more interesting. Maybe that's the... So if I have a curve here that somehow managed to intersect itself 3 times, so do something. Here's the real picture that I want to draw. In the universal cover, I have maybe 3 such arcs that pairwise intersect. Okay, so in this situation, I can sort of follow the same idea. Look at the ultra filters that come from points in the plane. So here I'll have one, just drawing the dual picture. Okay, so this is just the dual picture to what I see here. And I already see a problem, right? What's the problem? Yeah, the link condition, right? I have here a triangle that's not filled in. Well, actually, it is filled in. But it's filled in when I take all possible ultra filters. So what's hiding here, and that's really the problem with this perspective, is that not all vertices of the cube complex are sort of visible to us, right? So for instance, this choice of half spaces for the ultra filter is a vertex, right? It's a legitimate choice of DCC ultrafilter. Of course, I have to extend it to all half spaces. And what it produces for me is this missing vertex. Try it with a different color. So there's some vertex up here somewhere that makes this into a cube. So it works. It's just maybe more complicated than you might think at first. That's all I wanted to say. Great. So how can we produce more such examples? So you mentioned that these examples of curves on questions about this, yeah.
Very nice characterization of the vertices will come from the dual graph.
Which vertices will come from? I mean, we said the vertices from the dual graph are those that are visible. They come from, I mean, what kind of characterization are you looking for? Maybe that's the.
Like given a cube, how can you tell which corner of the cube is not going to be coming from a dual graph?
Yeah, I'm not sure I know how to answer this. You're looking for something that's you can see just in the pocket, but in the pocket you don't have this information, right? In the pocket you forget about how it's situated in space. You just build the thing. So, what? Sorry. Right. Okay. That's another great way of seeing this missing vertex is by doing a Reidemeister move, moving this arc slightly over here, and then you see this missing vertex. So, great.
Well, maybe that's this question. It's the answer is definitely the pocket corresponds to get the cube complex. And it's isn't that like if you
No, you're saying if all of them are visible, is that?
Yeah.
But they could. I mean, okay. It's yeah.
So that how you can do lines in space, all the combinations there.
Right.
That was training possible.
Right. It has to do with a specific picture. It's not something you can read in the pocket. Yeah, Danny wants to answer it. Yeah, thanks. He knows what's coming next. You know. So here's what Danny did.
You guys start asking more questions.
So here's a way of producing such things. So you can start with a C'16 presentation, small conservation presentation. So we saw yesterday what it is. Let's assume that all the relations have even lengths, just to simplify things for us. So here is one of those relations, right? We can form the presentation complex that Nir was talking about, and in this complex we have one vertex, an edge for each one of the generators, and we glue in those relation disks. And what we can do is just draw lines across. I said it's even, and then it's probably on. To draw a line across. So what this does for you is, well, it is something that's locally has a product neighborhood. Right? That's a good start. Right? So you do it for each one of the edges, and now you can play the same game. You lift this. So think of these as the curves on the surface, and lift this to the universal cover. Okay, so I don't know how to draw the universal cover, but in this space, I will see subspaces with the product neighborhood, and there is already something to prove, right? Because it might be that one of those things in the universal cover crosses itself. We don't want that, so should prove that. But basically, from this point, you just look at the corresponding dual cube complex. So I gave it as sort of an exercise. It's not an exercise. It's an involved exercise, but I'm sure that maybe that's the point to say the TAs. Where's Macarena? Yeah, Zach. Where's Zach? Zach and the TAs. So today at noon there'll be a problem session. So solve such things. Great. Yeah, and what's the point of all of this? Well, I should have said this, but when you build such examples, they actually come with the group action, right? The fundamental group of this the surface acts by deck transformation on the space. All of the things that I use are invariant under the action. Okay, so actually I get an action of my group on the POC set, right? And this produces an action of the group on the cube complex, the dual cube complex. Okay, so this is a way of not just producing cat-zero cube complexes, but producing such with interesting group actions. And let me finish with maybe what started all of this industry of like cubulating groups is Sagiv's work on codimension 1 subgroups. So here's the definition. So G, I'll take some finely generated group, and H, some subgroup of G, is codimension 1 if I take the Cayley graph of G, okay, with respect to some generating set, so finite generating set. Can I mod by H? This is the Shire graph. This has more than one end. What does it mean having more than one end? You can remove a compact subset of this space, this is a graph, and get more than one infinite connected component. So let me do a picture. Maybe let's do it for the, why did I erase this? All my pictures look the same, right? This is a circle with a line across. So here is G. Yeah. Here is my H, some subgroup. Okay, when I take this quotient, what I want to get is something of this form. So H will really become just one point in the space. But what I want is I want this space to have more than one end, meaning when I remove some compact part, I see at least two infinite connected components. So let's just assume 2 for simplicity. Okay, and when we have such a thing, we can pull back those subsets to here. So here is my yellow. Here's my blue. Okay, and I can start moving them around using G. Okay, so this is just one instance of this thing. Maybe this pair I'll think of as a half space and its complement. Right, so this would be H, be some H star. But I also want the thing to be G invariant, so I'll just move it by G. Right, so if G does something, moves this. So I have another, I don't know, GH and GH star. So this collection and this H that H is supposed to be the half space. Yes. This is a POC set. So, well, maybe should say that maybe it doesn't satisfy the finite crossing thing, but there's a way around this, and still you can build a cat-zero cube complex. So you can build a cube complex on which G acts. Cat-zero cube. Okay, getting to the end of the talk. You excited? Now is the real deal. We don't just want actions on cat-zero cube complexes. So this is, by the way, enough to get an action on a cat-zero cube complex without a fixed point, right? So actually equivalent. This codimension 1 subgroup and having an action without a fixed. This is what I give in. But moreover, when we have some kind of hyperbolicity to use, then we can get more. So I'll just state the theorem. So this is the theorem of Sagiv, and then the theorem of Bergeron-Meise. So we want more. We don't want just an action on a cat-zero cube complex. We want this to be, say, proper or co-compact. So Sagiv will tell us that if G is hyperbolic and H is a quasi-convex codimension 1 group, then the action G on this dual cube complex will be is co-compact, and this guy is finite dimensional. These are nice things that we want, but it's not enough. We want proper actions, and for this we have Bergeron and Weiss to help us. So here's the criterion for having proper action on a cube complex. So again, the setting is G is hyperbolic, and assume, maybe not all of you know what quasi-convex means. Ask me after the talk. This is maybe for people who know what hyperbolic groups are. But G is hyperbolic. Assume that for every 2 points, psi and zeta, in the boundary of G, there exists some quasi-convex codimension 1 subgroup, quasi-convex codimension 1 subgroup, such that the boundary of the subgroup separates psi and zeta, then G acts on a ket-0 finite dimensional ket-0 cube complex properly and co-compact. I say one more thing. You know what I'm gonna say, right? So this been used a lot to cubulate all sorts of groups. But I think maybe the most striking is, so you can use Kahn-Markovich. So what Kahn-Markovich do for you is, for a hyperbolic, closed hyperbolic 3-manifold, they actually produce contains many enough such things, quasi-convex surface subgroups, for you to apply this theorem. So actually, we get is that pi1 of a closed hyperbolic 3-manifold acts on a ket-0 cube complex properly and co-compact. Okay, I think I'll end here. Thanks.
Do you have more questions?
Yeah, maybe I'll ask something. This so this theorem gives you a particular cubulation for
Mhm.
G. If you have an arbitrary cubulation for G, do you know if you not necessarily have such quasi-convex sets?
Yeah, if G is hyperbolic and cubulated, you can use the hyperplane as this collection of yeah. Yes, Danny.
Yes, there's something similar to
Ask Danny. Great question. Yeah.
not going to take this.
Hmm?
Next question.
Well, Jill asked a question, right? I think there's some work of Rose and Manning that I think they spoke about in the last couple of conferences, where if you have a crummy, improper action on a cube complex, but the cell stabilizers are nice enough, then you can promote that so much better. Cube complex and it's virtually special.
That's not what he asked.
Yeah.
He asked whether you have
The converse of this, but that's yeah.
You said yes, but that's not true. We don't know, it's an open problem.
What do you mean? If you have a
Calculation of hyperbolic groups.
yeah.
You didn't say co-compact calculation.
Not
compact.
Okay. Sorry. I thought you were asking for just the converse of something like this. Something like this.
If the cube
The
complex
converse
is
is
co-compact, it's
yes. Okay.
calculation, then the answer to, then what you said is yes, that you were assuming that's be done.
Yeah. Sorry.
Everybody's sorry. So
We're in Canada. No, that's.
I'm sorry for asking that.
Let me just say, if you did not follow this last part of the talk, tomorrow it's a new thing, special cube complexes, much nicer, relaxed, new topic. Yeah.